Hello and welcome everybody. My name is Michael Schlichtig. I'm a researcher at Paderborn University and I will be presenting our large-scale study of usability criteria addressed by static analysis tools, which is a joint work with Markus Nachtigall and Erik Bodden. Let me start and explain the motivation behind this study. A recent code study performed by Veracode has shown that about 2/3 of all applications contain at least one cryptographic misuse, and this does not only hold for cryptography, but also is happening in all terms or types of coding issues. Software typically contains a lot of errors, and in this example with cryptography, this might be really serious as sensitive data could be leaked. And therefore, a lot of program analyzers have been developed, and program analyzers such as static analysis tools, and we are looking at static analysis tools in this study, they support developers in detecting potential coding issues. So far, research has shown many reasons why static analysis tools might not be used by developers. Here we have an example where we have taken the pain points in using program analyzers which were identified by Christakis and colleagues, and we categorized and highlighted them. So first of all, you can see that really the main or most frequently given pain points are related to precision, but then the largest fraction and number of issues, which is also very important, which were perceived by developers, are related to usability. Further on, also important pain points are related to time, so the performance of the analysis, recall, and some other categories or issues. But this really highlights how important usability is for static analysis tools. Further on, you can also see that the number of developers using static analysis tools has decreased within the past years, from 14% in 2018 down to 12% in 2021. And so far, research has collected mostly anecdotal evidence on usability issues with static analysis tools via surveys, interviews, or the researcher's experience. And to gather more empirical data, we decided to perform a large-scale study, which is our main contribution in this talk. And now I want to introduce our approach to research the state-of-the-art of static analysis tools with respect to usability. First of all, we started with extracting usability criteria from the literature. Then, after inclusion and exclusion discussions, we decided and found 36 relevant usability criteria, which we used to define an assessment grades for our evaluation. Furthermore, we also collected in total 243 static analysis tools from several lists in the literature with suggestions of good static analysis tools which should be used. And also there we went through several steps of inclusion and exclusion and ended up with 46 static analysis tools which we evaluated in this study. Now I want to say a little bit about the evaluation criteria. We grouped the 36 evaluation criteria into 6 categories following the recurrent usability issues which were introduced by Nachtigall and colleagues. These groups are related to warning messages, fix support, false positives, the integration of user feedback, workflow integration, and specialized user interfaces offered by the static analysis tools. And for each criterion in these categories, we predefined grades with which we rated and evaluated the static analysis tools, and these are typically yes for a fulfilled criterion, partially for partially fulfilled criterion, and no when a criterion was not fulfilled. And there are some cases like the runtime, which didn't fit into these grades, but there we had several grades or steps in time predefined. The other part was the collection of the tools. As I said, in total we collected a list of 243 tools and then went through several steps of exclusion. First of all, we had to exclude 81 proprietary tools because we were not able to gain access to them. But then there's another important figure here that you can see. In total, we were needed to exclude static analysis tools because they were either not maintained anymore or we were unable to install them, even going beyond just the standard documentation, but trying every trick in our sleeves. And these were 61 of the 243 tools, so about a quarter of the tools we were not able to install and use, which is already really saying something about the state of the art. Imagine a developer wants to try a static analysis tool and they need to put in a lot of effort, maybe hours to try to get it to run. Most likely they will not use it at all. So this is a real problem that we could find out early, even before the evaluation had happened. And then, in total, after all exclusion steps, we included 46 tools for our evaluation. Now I want to introduce you how we performed the tool survey. First of all, we created a setup with standard virtual machines. There we had one image for Windows and one for Linux, so that every tool was evaluated on the same machine. And then we followed a protocol for each tool. And this is, first of all, we searched for the website or GitHub repository. Then we followed the instructions for the installation from the documentation or the repository. And if we weren't able to install the tools following those instructions, we checked for alternative solutions. First, the first author. If the first author wasn't able to install the tool, then the second author also tried. And so unfortunately, oftentimes we put in a lot of effort and time just trying to get a tool to run. And as I said earlier, we weren't able all the times. So this is an unfortunate state of the art of static analysis tools. Some of them cannot be simply used. Then the third step per tool was actually the evaluation. We performed the evaluation with a multiple raters approach. The first and second author independently evaluated the tools. They did this by executing the tool, running the analysis on comparable projects depending on the program language, and also by checking the documentation. Then the results were collected, merged, and on disagreement, the authors had discussions for each criterion when they had a disagreement, and they went through their notes, looked again at the tool execution documentation to find proof to convince one another until they found an agreement and made their final evaluation. So this is the overview of our overall findings. It shows in total the 46 tools and the 6 warning categories. And we clustered the results, so a summary per category for each tool. They were rated either with a white circle, which means that they virtually did not fulfill the category of all the criteria that were in the category at all, then somewhat fulfilled if kind of partially the criteria per category were fulfilled, and then clearly fulfilled if the data indicated and showed that a whole category was clearly fulfilled. We split this table into two parts. On the left-hand side, you can see static analysis tools with graphical user interfaces, which were in total 24. And then on the right-hand side, command line interface tools, which were 22. And what is already striking out here is that the command line interface tools performed a lot worse. Now, I want to point out some main findings per category. For warning messages, a majority showed too poor performance in warning messages. For example, hardly any tool provides information about why it reports an issue. So there's no trace or path or internal reasoning given, which makes it hard for the developer to understand why there is an issue, and therefore also most likely not help in fixing the issue. For the second category, fix support, this has been the most neglected category, with 37 out of the 46 tools giving virtually all or no fix support, nearly no support at all, which is really unfortunate. Then for workflow integration, it has shown that CLI tools in general are problematic. They mean a media disruption. You have to switch between tools and it's difficult to use. And in total, only tools really stood out positively. For user interface, actually 3 tools stood out positively. And we saw that especially command line tools neglected highlighting of warning icons and user interface support. Throughout all tools, it was also visible that important features like searching through warning messages or tracking the progress of which issues have been solved by a developer so far were highly neglected. Then for false positives, only 12 tools allowed developers to explicitly report a warning as a false positive, which might be really helpful in terms of a false positive is reported. Therefore, team members already know I don't need to take, or they don't need to take care of an issue, and also limited support throughout the tools. For the last category, user feedback, I want to highlight some important features like adapting the rules. So the majority of tools allowed switching off some rules, so predefined rules of the tool, with the rules they used, which are the reason for reporting. So you can customize the rule set which was used, and 19 tools even allowed further modification or even writing own rules. So really customizable analysis at that point. But overall, we found that for a lot of criteria, there are good solutions. They may differ, but not many tools really provide a good user experience, and it is something to address. We hope that with our work, we can help for future work, for future development, to add improvements. And this brings me to the end of this talk. Just as a summary again, in the beginning, I motivated that usability issues are a main reason why static analysis tools might not be used. Then I explained how we went on to perform a large-scale study with respect to usability of static analysis tools. I showed you the collection process of tools and also of usability criteria, and in the end explained some of our main findings. With this, I want to thank you for your attention, and if you have any questions, please ask them. We'd like to discuss them, and just in case, here's my contact information. If there's anything you want to know, just contact me. Thank you.